Hello, welcome back. Today, let's discuss one of the problems from the 2025 British Informatics Olympiad Final, which concluded recently. Today, let's discuss the problem cold, or Cold War. So, this is the problem. I will explain it on a whiteboard, but as usual, I'll link the problem statement as well as my code and everything down in the description. But before we move on to the code, I'd like to note that this problem actually has two versions. So it has two versions. It has Cold War 0 and Cold War 1. Today, in this video, let's discuss the first version, and I'll have a separate video also linked in the description for the second version, or I guess it's version 0 today and version 1 next time, because programmers like to name things starting with 0. Zero-based indexing. Okay, so yeah, let's get right into it. Let's move on to the whiteboard and talk through the problem. The statement's quite simple. You've got a tree, and you want to, each node on the tree has a value, either a 0 or a 1. So a tree with binary values, and you have a target configuration of 0s and 1s that you want to get this tree to. So here, for example, this node has a 0 and it needs a 0, so it's correct currently. But this node 2 has a 0 written on it, but it needs to have a 1 written on it, so it's wrong. It has the wrong value. And similarly, these values are also wrong. So the node number 4 has a 1 on it, but it needs a 0. And you need to fix this, and the operation you have is to just swap the values on neighboring nodes. So you could take this 3 and this 4, for example, and the 3 has a 0 written on it, and the 4 has a 1, and you could swap those two. And that would actually fix both of these in this case, because the 3 would now have a 1, the 4 would have a 0, and they would both be correct. And the question is, what's the minimum number of operations you need to fix this tree? So you're given the tree, the starting configuration, and the target configuration, and you're asked how many operations you need to perform to fix to get the tree into the correct target configuration, the minimum number. So that's the problem. It's quite a neat problem. And yeah, let's jump right into the solution. This is the easy version of the problem. The harder version of the problem also asks you to output the swaps themselves that you need to perform to get the tree to the target configuration. But the easy version just asks for the smallest number of swaps. So how do we do this? Well, in this problem, you basically just have to guess the answer straight away. So what is the answer? What is the answer? The answer is that let's consider each edge. For each edge, let's say this edge right here. For this edge, let's count the number of 1s on each side of this edge, let's say. Right? Currently on each side of this edge. So currently we have 2 1s on this side, on, like this side of this edge. And we have, well, none on the other side. So this edge has this 0-2 split of 1s, right? And in the target configuration, we could do the same for 0s, but it'd be equivalent. So let's just focus on 1s. In the target configuration, we need 0 1s on this side, because, both the values that we need on this side need to be 0s. And we need 2 1s on that side, because there's a 1 here and a 1 here. So actually, we currently have no ones on the top side and 2 1s on the bottom side. And we need to have no 1s on the bottom side and 2 on the top side. That means we need to move 2 1s this way in the whole process of all these swaps. We need to move 2 1s upwards across this edge from the 4 to the 3. So what are we doing? We're considering the two the two components that would be formed if we removed this edge, and just counting the number of ones we have initially in each component and the number of ones we need to have in the target configuration in each component, and just comparing those. And so the difference between each of these values we'll call the imbalance of this edge. So 2 minus 0, or the 2 up here minus this 0, that's the imbalance of this edge. So it's just the difference. If you take this edge and then consider any one side of it and count the ones that we currently have on that side and the ones that we need to have on that side, that's the imbalance of this edge. And it'll obviously be the same if you count the ones on the other side minus the ones you need to have on the other side. If you take the absolute value, that'll be the same. So in short, for this edge, let's look at the imbalance. So if this edge has an imbalance of 2, because you need to move 2 1s across this edge, and equivalently 2 0s back across this edge. Similarly, this edge has an imbalance of 1. This edge has an imbalance of 0. This edge has an imbalance of 1 as well. So let me rub these out. So why is this imbalance significant? It's because whatever imbalance a certain edge has, you need to perform at least that many swaps on the edge itself, right? So if this edge has an imbalance of 2, then we need to perform at least 2 swaps across this edge, because the imbalance of 2 is telling us that there are 2 more 1s on one side of the edge than there need to be. So 2 1s on one side that need to be on the other side. And so we need to swap those 1s with 0s from the other side across this edge. And since it's a tree, there's no other way that those 1s could reach the other side. There's no other route around this edge that would be equivalent. So we need to perform at least 2 swaps on this edge. That's what that means. So that tells us that if we sum up these imbalances, the number we get, we need to perform at least that many moves throughout the whole process. Because for each edge, we need to perform at least its imbalanced number of moves on that edge, number of swaps. And the target, obviously, is to get all these edge imbalances down to 0, because it's equivalent for all the edge imbalances to be 0 to the problem being solved. So if all the nodes have the correct values on them, then all edge imbalances are 0, and vice versa. So is the sum of imbalances just the number of moves you need to perform? That's the question that comes to mind. And the answer is yes. So you could just stop here and just hope it's right, and just write some code and submit it and see if it works. Or you could try and prove it. So we'll prove it. But you could just stop here and decide to check by submission in a contest. But I always like to prove things. So let's prove this. So sum for each edge of the imbalances. So we're proving that the sum of imbalances across all edges is the minimum total number of moves we need. So we've already shown that the minimum is at least that, because any move reduces this sum by at most 1, because any any swap across an edge doesn't touch the imbalances of any other edges, and it changes the imbalance of the edge that you're swapping across by at most 1. Because if you swap the same two of the same value, a 0 with a 0 or a 1 with a 1, then that won't change anything at all. So the sum of imbalances will stay the same. And if you swap a 0 with a 1 across an edge, that edge's imbalance will change by exactly 1, either increase by 1 or decrease by 1. And all other imbalances of all other edges will stay the same. So this sum changes by at most 1 every move. And obviously, like we said, the final configuration has to have a 0, has to have this sum being 0, which is pretty easy to prove as well if you start from the leaves and work your way in. So all that remains to be proven, is that we can always reduce this sum by 1 in a single move. So we can always find an edge whose imbalance can be reduced by performing that swap across that edge, unless the sum is already 0. So let's call that type of edge an operable edge. So let's say an edge is operable. If you can perform an operation on it, if you can perform a swap that improves its imbalance, that reduces its imbalance, so it's ready to be flipped. So in this configuration here, do we have any edges, for example, that are operable? We have this edge isn't operable because it has a 1 on each side of it currently. So an operable edge has to have a 1 on one side and 0 on the other side, because otherwise swapping it immediately makes no difference. So the only such edge actually is this edge. This is the only edge with a 0 on one side and a 1 on the other side, but it happens to be operable because that's also the direction in which the 1s need to flow. So the 1s need to flow from this 4 towards this 3 across this edge. So the imbalance of 2 is, you can imagine the imbalance as having a direction. So this edge has an imbalance of 2, and this, whoa, that's not what I wanted to do. This edge has an imbalance of 2 in this direction, meaning that the 1s need to flow this way. So an operable edge is an edge that has non-zero imbalance, and the direction in which the imbalance is, i.e. the direction in which the 1s need to flow, there is currently a 0 on that direction of the edge and a 1 on the other side, so that you can actually perform this swap and improve the imbalance. And that's exactly the case here. So this edge needs 1s to flow from the 4 to the 3, and it currently has a 1 on node 4 and a 0 on node 3. So yeah, this swap would help. So in this case, there is such an edge. So we need to prove that there will always exist such an edge that we can perform this swap on greedily, basically, as long as the tree isn't solved. So we can keep performing these swaps just by looking for an edge that looks good, that will help us. And we need to prove that. And if we do, then all we need to do is just keep going through all the edges and finding an edge upon that is operable and making that swap and repeating. Now, doing that fast is a separate issue, but for this easy version of the problem, easier version, we don't need to do that. We just need to output this number. So in our program, we'll actually just go through all the edges, find their imbalances, sum them up, and that's it. Right. So actually, I'll walk you through this example just before we prove that, just to show you that type of edge always exists. So once we perform this swap between the 3 and the 4, we'll get a 1 here instead of the 0. we'll get a 1 here and a 0 here. And this imbalance is now down to 1. And now we repeat the process, right? We find an edge that's operable. In this case, we now have 2 edges that are operable, either this 4-5 edge or this 2-3 edge. And so we take either of them, let's say the 2-3 edge, we perform the swap. So this 1 swaps with this 0. This is back to a 0 now. And this edge imbalance is down to 0. Now this 4-5 edge is still operable. So we perform that swap, this imbalance drops to 0. As this value returns to 1, this one's now a 0. And then finally this 3-4 edge is again operable, has become operable again. So its imbalance drops down to 0 as we swap this 0 and 1. And now finally, this is a bit messy, but if you follow all the numbers, they're all correct. Yeah. So, it works for this example. Let's show that it always works. So our aim is to prove that there's, as long as the tree isn't solved, there's always an edge that's operable. Now, how we're going to do this is, well, we need a few steps. First of all, if we look at the leaves here, I'm going to perform a simplifying step, essentially. That's not actually strictly necessary, but this is the way I proved it, and I think it makes things simpler to remove some of the extra information. So if you consider the leaves, if a leaf has a value that it needs to have, so the target value is its current value, if it's correct, then the edge connecting that leaf to the rest of the tree will have imbalance 0. And this leaf isn't really interesting in the sense that if our proof is correct, that leaf will never be touched. And it makes sense that that leaf shouldn't be touched because it's just a node hanging off the edge of the tree with a correct value in it. You shouldn't need to, you shouldn't need to touch that. So we can ignore that leaf when looking for our operable edge. So ignoring that leaf won't change anything because it won't change any of the imbalances, is what I'm trying to say. So if we have a leaf like this in our tree, why don't we just ignore it? So we're trying to prove that we're taking a tree, we're assuming that it's not fully solved, and we're trying to find an operable edge. So first step, if it has any leaves that are correct, ignore them. So pretend those leaves don't exist. So just cut this thing off, just like toss it out, get rid of it. Now this removing leaves obviously creates new leaves, can create new leaves. So these new leaves might also be correct. So you might also be removing those and so on. So we'll keep doing that. We'll keep taking nodes off the tree until all the remaining leaves are now incorrect. So they have the wrong value left. I mean, you have to have some nodes left because otherwise all the nodes were correct, right? So you have to have at least one node left in the tree at the end of this. And, well, obviously it can't be one node left in the tree because if there's only one node with an incorrect value left, that means it's not solvable because the number of zeros and the number of ones in the target and starting configurations weren't the same. So you can't just have one node left. You have to have at least 2 nodes left. So the smallest configuration you could have left is with 2 neighboring nodes, one with a 1, one with a 0, that need to be swapped. That's the smallest one. So let's proceed in the proof. So now we've removed all these edges, just in our minds, theoretically. let's continue on our search for the operable edge. So let's root the tree arbitrarily, as long as the root is not a leaf. So let's choose a non-leaf root in the tree. You may say there might not be a leaf in the tree, but that's only in this case. So it's only in this case that I've drawn here, where both nodes in the tree are leaves. But that's not an issue because in this specific case, we can just deal with this case separately and say, well, the only edge left in the tree here is already operable. So we found an operable edge because, yeah, it's this one. Great. So now we can assume that there is a non-leaf node in the tree, so we just choose any one of them, and we root the tree at that node. So what have we got here? We've got to a point where we have a bunch of nodes left in the tree. All leaves have the wrong value written in them, and it's rooted at some root that isn't a leaf. So this might have been slightly confusing so far, but stay with me, bear with me. We're close. So now what we're going to do is we're going to start connecting these nodes. So imagine taking out all the edges from the graph, but then slowly putting them back into the graph. So halfway through the process, it might look something like this. So we'll take all the edges out of the graph, out of the rooted tree, I mean, with still, you can imagine the root will be somewhere up here. But these nodes are sort of, these nodes and edges, these edges have been temporarily taken out of the graph, and so have the nodes. And we start from the leaves, just the leaves. So this road here is the leaves. And we'll start putting the tree back together. So the diagram I've drawn here, some of the edges have already been added again. So we'll have something like this in the tree. And so we'll start with the leaves, so we'll just have this bottom row with no edges coming off it. And remember, these leaves, we've already recursively removed all the leaves that are correct, so all these leaves will have the wrong values written on them. So the notation I've used here is that the value inside the node is the current value, and the value on the outside is the target value. So this is a 0 that needs to become a 1. So we'll have some of those, and we'll have some 1s that need to become 0s. But in the leaf row at the bottom, we'll only have those types of nodes, one of those two, because they have to be wrong. So these are the leaves. And what do we do? So we'll start with just the leaves, and then we'll keep repeating this process. So we'll take one of the leaves and just connect it to its parent. So like this edge to this parent, we'll just connect this. Then we can take another leaf, connect it to its parent, and keep going until we run out of leaves. And then we can keep doing the same, but instead of with leaves, with subtrees. So we can now use this parent and connect it to its parent, and so on. As long as every connection we make has to be from a node to its parent in this new rooted tree that we've got. And the lower node, so the non-parent in that relationship, has to already be connected to its entire subtree below it. So we're not going to connect, say this node over here on the right, this 1, up to its parent before one of its children is connected to it. So that's one thing that we won't do. But other than that, we can connect in any order, and there always will exist such an edge that you can connect over. So you just keep adding these edges from nodes with completed subtrees already to their parents until you construct the whole tree. But we'll pause it at some point in a second. So you can imagine starting from all these leaf nodes, then drawing this edge, then this one, this one, this one, this one, this one, this one. Now we can draw one of these edges. Let's say now we have to draw, like I said, the next one we draw can't be this one because this child node hasn't had one of its children connected to it yet. So we have to draw this one. Or we could have drawn one of these. But now let's say we draw this one next. And let's keep going until the first time when we draw an edge between a 1 and a 0. And this is the critical point. Let's keep going until the first time that an edge is drawn between a 1 and a 0. So there must be at least one 1 and at least one 0 in the tree, because otherwise it just won't work. You know, if it's all 1s, then since the target tree and the starting tree have to have the same number of 1s, then the targets are all 1s and the starting values are all 1s, but then they're all correct, so the tree's empty, and we've already ruled out that possibility. So, you know, there have to be 0s and 1s, at least one of each. So at some point, if we repeat this process, you will connect a 1 to a 0. A value that a node that currently holds a 1 to a node that currently holds a 0. And when you do that, you'll realize that whichever one of them is lower, so whichever one of them isn't the parent, so in this case the 1, you know, its subtree, in short, this edge that you've now drawn will be an operable edge. So the first time you connect a 1 to a 0 will be across an operable edge. This guy. That guy's operable. And why? Well, if we count the number of 1s, if we just look at the nodes in the subtree here. So again, we take the child node, the one whose subtree has already been completely connected. And since this edge was the first edge we drew between a 0 and a 1, all of these nodes in this subtree must be 1s, right? They have to all be 1s. Because so far, only 1s have only been connected to 1s and 0s only to 0s. So these are all 1s, as you can see. But at least some of them have to have targets as 0s, right? They can't all have targets as 1s because at least the leaves among them, of which there must be at least 1, at least the leaves must have targets 0 because they have to be incorrect. We've removed all the correct leaves. So that leaves this subtree having as many 1s currently as it has nodes, but needing fewer 1s. So it needs at least 1 0, right? So if you look at the imbalance across this edge, it needs 1s to flow out of this subtree. And it has a 1 at the root of the subtree, and it has a 0 just outside the subtree in the parent. So this edge is an operable edge. So that's it. I mean, you'd have a exactly symmetric analogous proof, the dual proof, if you had a 0 here and a 1 here instead. So whichever way you connect the components, this will happen. So we've shown that in any tree that hasn't been completed yet will have an operable edge. So that's a very long way of saying that this solution works. And so the solution itself, you can just perform a DFS to calculate subtree sums for values, so how many 1s you have in your subtree, and then do that both for the starting configuration and for the target configuration. And then for each node, for each edge, you just subtract the number of 1s in the subtree in the starting and target configurations, take that absolute difference, and sum all those up for all edges. And that's the solution. So yeah, let's just take a look. This will be in the description. So main, ignore this just, input output stuff. The main solution is, it's very very short. You input everything, and then you have these two vectors. You have these two lists of values, target value and current value, which you've input, and you have children, which is a list of children for each node. So for each of these two, for the target values and for the current values, you call this function, which computes the subtree sums across them. So it returns another vector, which is the subtree summed versions. I mean, how does this work? It just calls a recursive DFS. And, adds the child's value to the node's value. So it's pretty simple. And then once you've done that twice, for the target and the current value, you just go through all nodes, take the difference between current value and target value across that edge. Iterating through all nodes is this basically the same as iterating through all edges here. And I've used the node indices as the edge indices, basically. So we're just iterating across all nodes and saying who's in my subtree, and your subtree is equivalent to considering every node subtree is equivalent to considering every edge's child subtree, since it's a rooted tree. We will also consider the extra edge from the root to nowhere as well, but that will be a balanced edge, so we don't have to worry about that. We don't even have to skip the index. So yeah, we add this to the total number of moves and then print that. That's it. That's this problem. Somehow I managed to explain it badly, even though it's supposed to be very short to explain. It's just one concept. You have to, it's harder to find than to explain technically, but I somehow did it the other way around and made this a bit too complex. But hopefully you got that. So this is Cold War Zero. As I mentioned, there's a harder version of this problem where you actually have to output the swaps. And if we consider the proof we used here for the existence of an operable edge, that doesn't really help you for finding the operable edges quickly and efficiently, because it's quite a strange proof. You're not going to run this thing every time you make a new operation. Every time you perform a swap, you're not going to rerun this weird tree connection algorithm to find the new operable edge. One thing you could do, right, to find all these swaps is just go through all the nodes. Sorry, go through all the edges, manually check whether they're operable or not to find an operable edge, perform the swap, and then repeat. So that would be an n-squared program. But it exists. It is an option. So that's the starting point. And so if you're interested how we actually find these swaps, then check out the next video. But otherwise, that's it for Cold War Zero. Yeah, this was one of the easier problems in the Olympiad in the final. But still not solved by most, so an interesting one. And the idea itself was quite neat and quite short. So yeah, that's it for Cold War Zero. See you later for Cold War 1.